Hello and welcome back to another lesson in the video series. Today we're going to be discussing the combined effects of diffraction and interference of two waves. You should recall from the last video that diffraction was the process shown here where a plane wave passes through an opening and creates a circular wave of the same wavelength and frequency on the other side. You should also recall that interference was when two waves overlap and create a third wave. You should also remember from another video lesson that interference is when two waves cross over each other and create a new wave based on the sum of the original two waves. We're now going to see what happens when two waves diffract through this boundary and interfere with each other, and what pattern will be visible based on frequency, wavelength, and slit distance of these two openings. What I'd like to do now is show you this same process in the three-dimensional view. So I'm going to clear the waves and change the perspective. Now I'm going to start the simulation. And what we're going to notice is that as the plane waves arrive and hit the barrier, each plane wave creates its own diffraction pattern. But what we're observing here is the overlapping of two diffraction patterns which create some highs or maximas here, here, and here, and some lows, some minimas here, here, and here. So what we're seeing is a third kind of wave. We have two original circular waves coming out, and when they overlap each other, there are areas where they are positively or maximally interfered and constructed, and there are areas where they are minimally constructed, or you would say destructed. What I'd like to do now is take this scenario and put it in a three-dimensional view and allow you to see that this barrier that has two holes in it will create two overlapping diffraction patterns. Let's take a look at that. So here come the plane waves, and now they begin to come through the hole. They are diffracting, and you could see their circular patterns. But here's a new pattern we haven't seen before. We have a very high point here, and all of a sudden a very low point here. A very high part of the wave here, and a low one here. And they happen to be very symmetrical. Let's run this a little longer so we can let this fan out and take a look at it. Alright, there it is. We have in front of us two phenomena happening at the same time. We have the diffraction pattern, which is the simple circle that you get on the other side of the opening. And now we have interference. This is two-dimensional interference. Let's take this into the two-dimensional view because that's what we're going to be working with, and it's going to have its own unique picture. It's important to point out that these areas where I'm mousing over have a very dark banding, whereas these areas now have a very light banding. So you have the one down the middle. That'll be called the central maximum. And then you have these first order maxima because they are the first ones to appear after these seemingly blank regions. And these blank regions are blank because the waves, they have canceled themselves out in these places, but have built themselves and constructed in these places. We're now going to build these wave patterns together step by step. What you see in front of you are the two circular patterns that are created when each wave passes through a hole or a slit opening in a barrier. S1 represents the point of origin of the first diffracted wave, and S2 represents the point of origin of the second diffracted waves. The solid lines that you see here in front of you, these represent the wave crests, and the dashed lines represent the wave's troughs. There is a very simple formula for understanding constructive and destructive interference. If two crests or two troughs cross each other, you get a bigger crest or a deeper trough. However, in destructive interference, Whenever a crest and a trough meet, they cancel themselves out. All right, let's build a diagram. Here I have in front of you a blank template of overlapping diffraction patterns. And here we're going to use the constructive and destructive interference template. Crests over crests, troughs over troughs, they make a constructive or bigger wave, and crests over troughs make a destructive wave. So we're going to start right in the middle. I've moved our rules up to the top corner so we will remember what constructive or destructive looks like. I've started with this green dot, exactly halfway between source 1 and source 2. And it turns out that you have a dashed line crossing a dashed line. So, that's trough, trough. That's a constructive interference. Now, if I move straight ahead to the next crossing, you will notice that two solid lines cross. That's crest and crest. So what I have here is another constructive interference point. If I move straight beyond that, I see that there are two troughs that are crossing. So that's another constructive point. If I move straight ahead, here is another constructive crossing. So if you notice a pattern developing so far, all of these lines down the very center are constructively interfering. That means that the wave down the center is the tallest. The amplitude of that wave will be the highest because you can see all of these points are constructively interfering. Now let me connect that with a line for you. So I've connected all of these points with a blue line just to show you that this is the central maximum. Now let's move over to the side by one wave crest and let's trace out what we get from that pattern. And so on. And you could see that this line is beginning to fan out and move to the left. Let's take a look at this right side. You should expect to see a symmetrical line, a mirror image on the right side as you do on the left. Let's build that together. These are the lines that you observed, your central maximum, and then you had a tall wave on each side of it with an empty space in the middle. Let's build another wave on each side. Okay, and there we have it. Now you should be able to see a very clear pattern. Now I'm going to build the destructive interference patterns in red. I'm going to start building the destructive interference patterns wherever a crest meets a trough. And I'm going to start from the blank space between the two crests right off center. And I'm going to go forward and see that there is crest meets trough here. And there again. I'm going to fill in this whole chart for you, and then we're going to come back and take a look at what that looks like. Okay, here we have all of the destructive interference points. Everywhere a crest meets a trough, I put a red dot to show that those two waves cancel each other out. Let's take a look at what happens when we overlay the constructive and the destructive points. This is a snapshot of the constructive and the destructive interference points. You follow the green lines up, you follow the red lines up. I'm going to try to fill those in for you. Here we have the green constructive interference lines and the red destructive interference lines. These are the parts of the wave that in the green zone add up and make bigger waves, and here are the parts that are in red which destruct or subtract away and make smaller waves. And right on the center line where these dots are being connected, there is actually no wave at all. That's where a crest meets a trough, and they completely cancel out. But on the green lines, it's where two troughs meet or two crests meet, and that gives an additive effect. Okay, let's take a look at a problem on diffraction interference. This is number 22. It says two speakers, S1 and S2, are operating in phase at the same medium, produce a circular wave pattern shown in the diagram below. We know what this pattern now is. All the solid lines are the wave crests, all the dashed lines are the wave troughs. And wherever solid meets solid, you have constructive interference. And wherever dashed meets solid, you have destructive interference. In this diagram, I've chosen to highlight for you the central maximum. So look right between the two sources. Solid, solid, dash, dash, solid, solid, dash, dash. So look at the center line and see that constructive interference takes place and you have a large central maximum. Here at points A and D, you have constructive interference. But if you follow this over to the left or to the right, and you'll see that dash solid, solid dash, that's destructive interference. So points B are in a zone of destructive interference. And you can see the curve moving away to the left and to the right, off center. These are zones where the wave has canceled itself out. In this last diagram, I've drawn it again. I've made blue the central maximum and all the maximas, and I've made the dashed red line the destructive line. I want to follow this out to its logical conclusion and just show you something here related to the amplitude. This purple wave is, in fact, a representation of the third dimension. If you were to look at these waves as we did over here in the simulation, you can see that the center wave is the tallest, and then there's a dip on each side, and then the next maximum wave is not as tall. And so in our diagram over here, you can see I've drawn this schematically. So the central wave, the central constructive interference, is the tallest. Then you have a cancellation on each side. Then you have another additive construct, but that wave, the first order of each wave to the right and left of the central maximum, not as tall. Then it dips down on both sides and cancels. Then it rises a little bit on both sides, but not as tall as the one before it, and so on until they are canceled out all the way to the ends. And they have diminishing amplitudes as you move further and further away from the central line. Okay, I want to extend this concept into light waves, and even though we're not in the light waves chapter, it's a good time to bring this up. If we were to send a beam of light through 2 points and the holes were separated by a distance apart, you would get the exact same pattern of overlapping waves. However, instead of water waves, and you're dealing with light waves, you would not see a tall water wave, you'd see a central bright wave. Here's what it actually looks like. If I sent a red laser through the 2 slits, I get bright and dark spots on each side of a central bright spot. Here it is for a red laser, here it is for a green laser, and here's that graph I drew for you. The central maximum of intensity, and then as it moves to the right and to the left, it decreases. So we can actually tie this concept to waves for water, sound, and light. Let's take a look at what I have here. The constructive interference. If this was a water wave, it would be a tall water wave. If it was sound, this is where the sound would be loudest. And if this was a light wave, this is where the light would be brightest. Now all the destructive parts, if it was a water wave, it would be a flat spot on these red dashed lines. But if it was a sound wave, it would be a quiet spot on these red dashed lines. And of course, if it was a light wave, it would be a dark spot on all of these red dashed lines. So the central maximum has the greatest amplitude. For water, its height. For sound, its volume. And for light, its brightness. And as you move to the right and to the left, you have these spaces of nothing. That's the cancellations. And then you have diminishing amplitudes as you move away from right and left of the center line. This was a very complex topic. I thank you for watching and I hope you enjoyed it. We'll see you in the next video.